Alrighty, corn children. 6.1, part 4. Area between two curves integrating with respect to y. We're going to see why we need to integrate with respect to y. Why this is a good idea. It's pretty much based on the fact that our two curves are going to lend itself towards that integration. So, it says find the area bounded by x equals 3 minus y squared. Okay, so first of all, it's not a y equals x, it's x equals y. Interesting. This is going to be a sidewards parabola opening this way starting at 3. If you aren't sure of that, you can go to your graphing calculator, type in y equals 3 minus x squared, but then you have to picture it reflecting over the line y equals x. So you're going to get a downward opening parabola, which you then have to reflect over to this side. So it's a little tricky right there. And the other line, or the other curve, is a line y equals x minus 1. So I've drawn them here. Here's the parabola. Here's the line. Now, I want you to think back to when we did area and we did Riemann sums and we did our rectangles in there. If I set my rectangles up vertically, in other words, where the width is horizontal, so the width is a small change in x, there's going to be a problem with setting them up this way. From this point of intersection to this point of intersection, the line would be on the top. The rectangles would go from the line to the parabola. But after this point of intersection over to 3, the rectangles would be from parabola to parabola. We would have to take this equation, solve it for y, which would be involving a square root with a plus or a minus. The plus would be the top half of the parabola, the minus would be the bottom half, and I'd have to set up these two integrals. From here to there, line to parabola. From there to 3, parabola to parabola. It can be done, but it's a heck of a lot of work. Consider with me instead. What if we fill this area with rectangles not stacked right to left, but stacked bottom to top? What? You can do that? Yes, you can. And please notice that the width of the rectangles is vertical. It's uppy-downy. So the vertical change here is a teeny tiny change in y. And we will stack our rectangles from the bottom to the top, meaning my limits of integration will be found on the y-axis. It will be dy with respect to y. And when we integrate, until we find, well, I could just tell you where these are. This is the point -1, -2, and we could solve to get that, but here's the idea. It is the y-coordinate -2, not the x-coordinate, that becomes my limit of integration. This point of intersection, I can do the work for you, but it's the point 2, 1. It is the y-coordinate of 1 that becomes my limit of integration. We will integrate from -2 on the y-axis. Get rid of that dx in there. I erased those. All the way to 1 on the y-axis with respect to y. But what do we integrate then? Well, we're going to integrate, instead of top curve minus bottom curve, we will integrate the right curve minus the left curve. And these are going to need to be functions of y. In other words, I will need the equation x equals y stuff and x equals y stuff, the right minus the left. Well, our right curve is the parabola, and our right curve is already defined as a function of the variable y. It is not y equals x, it is x equals y stuff. So I'm going to name this f of y. It's a function in the variable of y. Okay, what about the left curve? Our left curve is going to be this line. This will be the g of y curve. But there's a small problem. This function is not defined as a variable of y, it's in the variable of x. Yeah, but we took Algebra 1 and we can rearrange this. I'm going to move the 1 to the other side. If I rearrange this equation, it becomes y plus 1 equals x. And I will call that g of y. Look at it. It's a function in the variable of y. No way. We can totally do this. So here's what this becomes. We already have our y limits of integration with respect to y. We would integrate the right curve, which was my f of y, minus, be careful with the parentheses because there are two terms, the g curve, a function of y. No way. Now, points of intersection, it's going to be the same old story. In order to find our points of intersection, we need to be able to set these equal. Because of the way this is set up, I would probably use direct substitution. I would fill x equals this stuff, there's an x, I would fill that into x and then solve that quadratic for the y variables. If you need me to do that when we get together, we can do that, but I think you can figure that out. So, from here, we integrate just like always. You can distribute the negative, you can combine like terms, you can integrate by hand. If you had your graphing calculator, we could finint this. I might type in x's, but we would really understand that they're y variables. So if you want to finish that thing out, the answer ends up being an area of 9/2. All right, there it is. That's a little sneaky. Good luck with those.